Okay, so today we're going to talk about distributed systems. So in general, when we talk about processing lots of data, we'll often have to use multiple machines. So we could do an entire class on distributed systems, but it's going to be an introduction of the main concepts. So distributed systems. So when we're processing massive data, we need to use distributed systems. We spoke about this idea of having one machine that's n times as powerful versus n machines that are equally as powerful. So being a bit more formal about what this means, we have parallel versus distributed systems. So a parallel system often has shared memory somehow. In fact, also the processors might refer to different modules of RAM, but they can somehow share data across the different memory. So this is a parallel system, whereas a distributed system will often refer to it as being shared nothing. So they don't share anything. They have their independent machines that have some way to communicate between themselves. So this is what we mean by a distributed system. We'll mean a shared nothing system. So we have independent machines that collaborate to form a system. So what is a distributed system? A distributed system is a system that enables a collection of independent computers to communicate in order to solve a common goal. Okay. So we have four machines here. They're somehow communicating. They can also communicate pairwise. They're sharing some information between each other to address some task or solve a goal. So they have three important properties. One is concurrency, that the machines are processing or working somehow concurrently in parallel, let's say. And the second is independent failures, that individual machines can fail, but the other machines will continue to work. So we have this notion of independent failure where individual machines can go down, like so. And we have the idea of no global clock. So this means that these machines will never have exactly the same time, right? So we could say, okay, they're going to have pretty close these days to exactly the same time. But if we think about it in terms of a clock cycle in a processor, it would be quite difficult to synchronize the clocks at that level of precision. So there's going to be somehow some difference in between the machines in terms of the time at some level, be it, for example, nanoseconds or clock cycles in the processor. So they cannot agree on the exact time. So this creates some challenges. There's various challenges of distributed systems that might not seem obvious at first. So to illustrate that, there's this analogy of General's problem, two General's problem, and General's problem, Byzantine General's problem. So we'll just talk about two of these abstractions. So the analogy here is that we have two generals. In this case, I think we have the bad guys in the US Civil War. They want to attack across a river. So they want to basically be able to force back the defenders in this river, and they want to meet up on the other side. So the idea is that they have two different armies here, and what they want to do is they want to attack at the same time. We're going to assume this, right? So if they attack at the same time, then they will be able to meet up and have success. But if they attack at different times, then the defenders will be able to rebuff them or to keep them on this side of the river. So the question is, how can the generals who are in remote areas, there's some distance between them, how can they coordinate a time for the attack, right? So they haven't yet set a time. So obviously, we send messengers from one side to the other, right? So we'll assume that this general here is the leader, and even choosing who is the leader is quite difficult, but in this case, we can simplify and say that, okay, we have a leader here who's going to propose a time. So again, they have clocks, they have time, but they have, first of all, slightly different times. So depending on how much tolerance there is for attacking at the same time, this is already a complication, right? So now they need to agree on a time to attack, but let's assume that they have more or less the same time. Even assuming that they have a global clock, they can agree on the time. They can send messengers on horseback, but these messengers can be killed en route. So they can be killed on the way. So how can the generals coordinate a time for attack in this situation? So the issue is that, okay, let's say the first general could send a message. Let's attack at 12:50. Yeah. But now this general is like, okay, the messenger will have enough time to get there. The second general should get the message, right? But there's a problem, which is, what's the problem? So if this general sends off this messenger at 12:50, should this general attack at 12:50? If he attacks without the other general, the attack will fail, right? So the problem is, yeah,
The issue is that the first general doesn't know if the message is intercepted. So
right. Yeah,
it's
exactly. So
confusing.
exactly, yeah. So that's problematic. So how could we solve that? We could say, okay, well, they maybe beforehand have some sort of procedure or military book that tells them how to solve this, some algorithm. So let's say that this general then should send back an acknowledgement and say, okay, 12:50, okay, let's do it, right? So what's the problem now?
Um, the second general doesn't know if the his messenger has been killed or not.
Exactly. So now this general doesn't know if the acknowledgement is received, so it doesn't know if this general is going to attack at that time or not. So the obvious solution will be that this general should send an acknowledgement of the acknowledgement, and this general should send an acknowledgement of the acknowledgement of the acknowledgement, and so forth. Right? So okay. So how do we solve this problem? We get into this recursive. We get into this recursive issue, right? So how do we solve this problem? Um, and you can, maybe think about it and you can think of different ways, if they had phones or they had telegrams or they had, the app Telegram, they could maybe, send messages more instantaneously, right? But in this sort of situation, really there's no good solution. You just have to try to make sure that the messengers don't get killed. Maybe you send lots of messengers at once. Maybe you try to find a better form of communication, but really you have to, somehow have a reliable way of communicating to coordinate a time for the attack. So this is obviously an analogy of a distributed system where we have two machines that are connected by a network, and we can have network failures and so forth. So the degree to this, to the extent to which this might be a problem is different depending on the media of communication. And obviously sending messages over a network should be more efficient than messengers on horseback, but the same principles still apply. So we get some idea that actually, okay, this is kind of hard. It's hard to build these systems where messages can fail between systems. So there's even tougher versions of this problem. So we've already been generous and assumed that they can tell the time, that they have an agreement on what time there is within the tolerance of the attack. But there is an even tougher problem, which is called the Byzantine generals problem, which there's various ways this is expressed, and usually there is multiple generals, like n generals. But in this case, messengers can be replaced with spies, which means that messengers can be intercepted and they send another messenger with fake time or some false information. And so this is an even tougher problem. This would be essentially similar to, a machine that's been hacked or some software that has gone wrong, or some buggy software, where what the information we're getting is not even correct. Okay, and this is an even harder problem. So in this case, all we can try to do is try to make sure the messengers don't get killed or replaced. There's really not much we can do. So there are some consensus protocols that help in the case of n generals to try to make sure that if at least a certain number of messengers are trusty or trustworthy, that we can have a certain number of those channels attacking at the same time. But we can see that actually this is a hard problem and there's no easy solutions. So again, this is now an analogy of a distributed system where the messages in this case not only fail, which are called fail stop errors, but also they can be incorrect. They can give false information. And we'll speak a bit more about how to handle these sorts of errors later in the course. But just to give an idea of some of the problems that we face when we consider distributed systems. Any questions or comments or? Okay, so you can start to think about, how this affects you in your real life if you're trying to organize with someone to go for lunch or something remotely, how you solve this problem, or why this isn't such a problem in practice, but at some level it is a problem. Okay, so what makes a good distributed system? Good distributed system, I'm going to mention 5 things. The first thing is that a user shouldn't have to care about the individual components of the distributed system, which is to say the individual machines. A good distributed system should appear transparently as one system. Like when you go to search Google, you don't need to say on which machine within Google indexes the web page that you're looking for, right? You just send Google a request and it's all transparent, and then Google internally will figure out which machines to ask. So transparency, it should look like one system. So you want to abstract how different machines are accessed, where the machines physically reside, where they're plugged into the wall, what kinds of different software and hardware they're using, and so forth. So how can you do that? You can do it by using, abstract addresses like URLs or different types of abstract addresses that don't depend on the physical location of the machine. And you can use APIs or higher level interfaces that can be implemented in different ways for a more modular and transparent system, and so forth. So transparency is the first criteria. Second thing, we want some flexibility, right? We want to be able to add or remove machines quickly and easily. So we want to be able to add in more machines if we need more processing power or more storage or whatever it is. And likewise, we want to remove machines. That's particularly important because we might have errors, for example. And we want the system somehow to be able to quickly incorporate the new machine, or to get rid of the machine that has stopped working, for example, or is being removed. We want to avoid things like when we add a machine having to restart the entire thing, right? So if you imagine if Google had to restart their entire distributed system every time they add a new machine, that wouldn't work. We don't want lots of work associated with adding different machines. So how can we solve this? For example, platform independent software. For this reason, Java is particularly popular in big data for distributed systems, because you have a JVM that gives you this sort of platform on which you can develop software. Also load balancing. So essentially, if you add a new machine, your distributed system should be able to recognize that and start to assign it work, or start to assign it data to store, whatever. So you want this to be automated. Third element is reliability. So we want to avoid failures. We want to keep working in case an individual machine fails. So if one of these machines here fails, what we want to do essentially is keep working, right? We want to keep going. So every time a hard drive dies in Google, for example, it's not like the entire Google search engine falls down. Right? It keeps going. I'll just ask another machine with the same data, for example, to serve the results. So we want to avoid downtime, and we want to avoid inconsistency. So, if a machine fails, maybe instead of just being down, maybe it starts producing nonsense, right? Maybe it just produces incorrect results, Byzantine errors. And for that reason, we want to avoid inconsistencies. So how do we do this? We can use replication, where we keep multiple copies of data, or multiple machines can serve the same role. Flexible routing, which means that, this is in general important in the internet, for example, where we don't always go through the same route. If one machine is down, like one road is blocked in the network, we can go around another road to get to the same destination. Consensus protocols, which help us to agree on a value within a distributed system, like what time to attack, right? These sorts of consensus protocols try to address these general problems. these generalist problems, right? So we'll see a little bit about that later in the course as well. Performance, it should work quickly. This one's maybe kind of obvious, but we'd like our distributed system to be able to process, find data quickly, right? So there's not much to really say here. We want to avoid latency, which is the time for the initial response. We want to avoid long run times. We don't want things to process for longer than necessary, at least. We want to avoid waiting. How can we do this? We can try to reduce the amount of data that we transfer over the network, try to assign more resources to something that's running slowly, and so forth. So the final element that's important is scalability, which is to ensure that it's a good characteristic of a distributed system if it can scale. So what does this mean? It means that we can scale in terms of adding more machines or sets of machines, let's say. So that's one aspect of scalability. One more, I think. And as well as that on the other side, that we can scale in terms of the number of, so this forms one distributed system still, and we can scale in terms of the number of clients, the number of users of the system. One more. Okay. So how can we, what do we need to avoid? We need to avoid bottlenecks. For example, relying on one machine, like sending all of the data always through one machine, having one machine control the entire distributed system. If it's very large, that would be a bad idea. We want to avoid as well things like pairwise messages, where we don't want every machine to be contacting every other machine, because that becomes quadratic, right, and squared. All these connections that we need to maintain. So how do we address scalability? We can think of things like peer-to-peer, which I'll talk about in a second, where we avoid central servers, central nodes. We can think about direct transfer of data, so we're not, transferring data always through the same machine. We can think about distributed indexes that allow us to quickly locate particular data or particular resources we need within the distributed system, and so forth. Okay. So these are the five elements we could mention about what makes a good distributed system. So maybe it's kind of intuitive enough, but it's still useful to reiterate these elements because it affects the design of distributed systems in different ways. Okay, any questions or doubts? Okay, so we'll talk about a couple of different types of architectures of distributed systems. And I'm going to talk about two that are essentially on both ends, are two extremes in the choices of architecture. So the first one is a client-server architecture, and this is probably the most simple, in the sense that what we have is a client and a server, and the client makes a request to the server, and the server acts upon that request and responds with some answer, right? So this is something we're very familiar with. So any examples of client-server models, any applications that use client-server? Yep, so Google would be one example. There are many, right? So web in general, you have web servers, right? So your client sends a request over HTTP and receives an email as well. You have an email server that manages your SMTP server or whatever. Ukursos would be another application. Yep, so you have all the forum and all the database sitting in the central location, and people request the forums and get the responses. Things like Dropbox and so forth. It's probably the most common model that we use nowadays. Also part of the problems we face with data, and that we have these massive servers that are somehow housing all of our data, and all of our lives and everything. So just to mention, sorry, I went forward here. This server here, I don't want to say server as just one machine in this case. I mean that a server can have multiple machines, right? So here we see actually the server has 4 machines, like the way Google obviously operates on lots of different machines. So the server here is just a service, something that, it's a service that's being offered in a central location. So just to emphasize that, if you may have heard of a 3-tier server before, I'm not sure, but essentially the idea is that we have 3 tiers in the implementation of, a typical, for example, web server or web application, where we have the presentation layer, where someone which receives, a HTML form or something like that, that receives a request from the user, and then it goes through a logic layer, which will transform the request to something like an SQL or a logical request, which will then go to the data layer where all the data are stored, and then it will, return through the logic. Maybe the logic layer will process the data further to add all the salaries or aggregate some data and create the final HTML page. So this idea here is we have a layer for data, logic, and presentation. So this is more about development of web applications, but I don't want to give the idea of the server as being the simple one machine running some application, right? The servers can be arbitrarily complex, and they themselves can be distributed systems. And the clients as well, I guess, could also be arbitrarily complex. But the idea is that somehow the requests are processed through a central server. Okay. So this is what we call a 3-tier server, 3-layer architecture, where we have data, logic, and presentation. Just to mention that these servers can be complex. So the server can be a distributed system, and I don't mean here that a server is a physical machine. In other moments, I might say that a server, talk about a server, I will actually mean a physical machine, which is a little confusing, but I'll try not to. Okay. So the next architecture we have is the peer-to-peer architecture. Or maybe there's questions about the previous part. Let me see what time it is. Okay. No questions? Okay, so we have peer-to-peer architecture. And essentially the idea is, if we compare it with client server, in the client server, the client interacts directly with the server, right? And when we go for peer-to-peer, we have peers interacting directly with each other, right? So if we look at it in a way, if we try to conceptualize this, what we'd say is that here we have all these different clients that are interacting with the central server. And here in the purest form of peer-to-peer abstraction, we could say that every peer is both a client and a server, right? It has some of the responsibilities of serving requests or being the server. And in other cases, it can ask things from its peers as a client. So it can essentially, each peer is somehow acting as both. So, okay. Any examples of peer-to-peer systems? I already see some in the chat. So Torrent is one. uTorrent, I guess, is a client, but Torrent is one type. Streamverde and Qubit, I've never, Qubit is quantum computing thing, but blockchain. And yeah, blockchain is good. So we have Torrent and blockchain. So, okay, the first kind of application we'll think about is file sharing, file storage, right? So the kind of typical client server or file server. So the typical client server application will be Dropbox. So we have Dropbox in the middle, and you have all these clients who are pushing data to it and downloading data from it, right? The kind of peer-to-peer analogy of that would be something like BitTorrent, where peers act as both the file server and the client. So I'll talk a bit more about how BitTorrent works a little bit later, but essentially there's no central location storing all of the data of BitTorrent. Everybody is storing a bit of the data in the network and serving their part of the data, and also requesting data from other peers. In terms of banking, so we have online banking. We have a central bank where clients interact with a central coordinating server, the bank, because we have our bank and we have all the clients, customers here using the bank, the central location. The kind of peer-to-peer version of that would be something like a cryptocurrency. based on blockchain, right? Or based on blockchain, I guess is the only. I don't know if there's cryptocurrencies that don't use anything like the blockchain, but essentially the peers act both as the bank and as the client. So specifically here, the miners are acting as the bank, but anyone can be a miner in the network. And then the clients are the people making the transactions. So another example, and maybe a bit more technical, would be, or less well known, would be SVN. I don't know if you've heard of SVN, but essentially it's an older version of Git. And the idea was in SVN that there was a central server that was somehow the authoritative version, like the canonical version of the canonical store of the version data. Whereas in Git, technically speaking, it's implemented more in a peer-to-peer system where the peers also have their own repositories, which they sync. So there's no kind of central coordination. Of course, you might say in Git, okay, I use GitHub and GitHub becomes a central repository, but there isn't really, this notion like there is an SVN of this central repository in the middle. So the question of whether Git is peer-to-peer, it's certainly more peer-to-peer than SVN. So a sort of confession I will make, and I'll give you a practical example, is that these architectures are slightly idealized, right? There's no clear separation in practice between these different types of abstractions. Okay, so we still have some time. So I'll talk about the first peer-to-peer type of coordination. And this is the basic one where essentially it's uncoordinated, we could say. It's unstructured. So if we want to do lookup, we need to do something called flooding. So what happens here is we have a bunch of devices that are connected. And we have mobiles and we have desktops and we have laptops and so forth. And within this peer-to-peer system, somebody is looking for, we'll assume this is a file sharing peer-to-peer system. Somebody is looking to see if anyone has a copy of Ricky Martin's new album. So this album is actually probably from 2013. I don't think I ever updated Ricky Martin's new album in the slide, but so the client here knows that someone in the network must have a copy of this. So how does that client find the people in the network? So most of the time, essentially, the peers can't connect to everyone because that would be n-squared connections. And if you imagine a very large peer-to-peer system, it's just infeasible to have connections open to all of the clients, right? So, and there's no central index. There's no central server to say, this client has these data and so forth. You don't have this central directory. You essentially have nothing. You just have every machine is connected to some neighbors, right? So how do you find the data? Essentially, the only thing you can do is ask your neighbors and ask their neighbors until they find something. So in this case, it's a pretty popular album. So it doesn't take too long. Okay, maybe even if they get lucky and they find that a direct neighbor has that album. But and then essentially the data would be transferred. Once the metadata or the file is found somewhere, then the actual album itself can be transferred. So what happens if they look for maybe something a bit more rare, Pixie's new album, which is again from 2013, I guess. So they have to ask their neighbors, and their neighbors will have to ask their neighbors, and their neighbors will have to ask their neighbors. And we'll see that just for this simple request, the peers have to end up, a lot of messages have to be sent to locate that the album that this peer is looking for is available on this peer here. Okay, so once that's done though, once the metadata are found, then there can be a direct connection established between the peers in order to transfer the data. Okay, so it's time for a break. Any questions or doubts? Is Tor peer-to-peer? I wouldn't say so. So in Tor you have, I think it's maybe one of those cases where you have, it's kind of a mix of both, because you still have the notion of this server, someone is serving this website, right, or this content. But you also have the notion of these proxies that are different layers of encryption that are somehow stripped off as you go through the network. I mean, it's a good question. I think it's not something you could easily classify as one or the other. It probably has elements of peer-to-peer and elements of client-server, which is also the same for BitTorrent, which I'm going to talk about in a little bit. But most real systems don't very neatly fit into one category or the other. Yeah, so it's a good question. I would say probably it's a mix of both. Okay. Other questions or doubts? Okay, so see you at 3:10. Okay, so in the last slide, we saw that the unstructured peer-to-peer system, it's difficult to find the peer with the correct data. We have to send a lot of messages. So another option is to use a structured or central peer-to-peer, where a central node stores an index of which peers contain which content and their addresses. So in this case, the peer registers that its address and says that it has a copy of Ricky Martin's new album. Then when another peer requests content, they can request it from the server, and then the peer can actually connect directly to the peer with that data. So the difference with the client server model is that it's not the server here, the central node, serving the data. It's rather just serving as an index for the network. So advantages and disadvantages, any ideas? So one advantage is obviously that now we can more easily find peers that contain certain content. So I've started the video. Thanks for the mention. Any disadvantages? So data coordination wouldn't be such an issue. So we can still send the data like from peer to peer as we did before. Yeah, so one issue would be the bottleneck. So essentially the central server needs to be, quite scalable. It needs to manage, if this were a very large network, it would need to manage a lot of data about peers, which ones are active, which ones are connected, which ones are not, what content they have, and so forth. So a bottleneck is an issue, but there's an even more practical issue. Privacy as well would be, yeah. So essentially the central server now knows which peers have which content, which is a major, let's say, social issue. Another kind of social / technical issue is that we have what's called a central point of failure. So this is true of any client server type structure, right? But in this case, it's a big problem. Yeah, so we have this problem of this node can go down and then the entire network will fail. So this has been a problem. If you've heard of Napster, Napster was, this file sharing site where essentially there was a central index used to remember which clients contain which data, right? So what happened in this case was essentially that a central server was targeted and brought down by law enforcement because they felt that the service was primarily used for illegal file sharing. So the law enforcement managed to bring down Napster by targeting the central index server, and that was essentially the end of Napster. So this is a sort of a disadvantage, even aside from law enforcement and so forth. Essentially, the idea is that if you lose this central index, then the network will cease to function. So also issues with respect to privacy, this central node can become a bottleneck as well. These are also valid disadvantages. Yeah. So a very general, very brief sort of other type of network we can have is a hierarchical network where we have something like super peers and we have peers. So a super peer, maybe you have something in your university that is talking with other universities, and then the normal peers might be students who connect to the university super peer. Or maybe it's not really the same thing, but you could imagine maybe in something like cryptocurrency, you have these super nodes that contain the entire blockchain, and then you have these clients that have some wallets, or maybe these super peers are doing the mining, for example. So anyone can sort of be a peer or a super peer. It's not that there's some condition on this, but essentially the idea is that there are some super peers that are more stable, that are maybe always connected, and this is another kind of general way of organizing a peer-to-peer system. Advantages and disadvantages. Well, we can maybe say that it's a more complex structure to manage. It's sort of, how do you delegate? How do you choose who are the peers, who are the super peers? You might also have, if one of these super peers goes down, it might cause a lot of disruption without actually, ending the distributed system, without, completely collapsing the network. It might cause a lot of disruption. For example, if these peers are only connected to a super peer, then for these peers, it might be quite catastrophic if the super peer goes down. So it's sort of like a balance between, the pure peer-to-peer system and the central directory type peer-to-peer system. Another option is structured but distributed. So there is a structure called a distributed hash table, a DHT, that is sometimes used in peer-to-peer systems. And the idea is a classical hash table idea that we have keys and values. So a distributed hash table, distributed dictionary, however you'd like to call it. So we perform a hash on the key, and then we can do insertions with the key value. And the idea is that different peers are assigned different ranges of keys. Okay. So essentially, here we have sort of a hash table where we can go down and find the peers that are indexing the values. The values can be anything, right? They can be tuples in a database, they can be specific types of files, whatever we would like. So we have these different we have these different ranges here, and then clients or peers are assigned different ranges. So in this case, for example, we might associate with Martin's new album 000, Pixie's new album might be 111. Okay. So advantages and disadvantages in this case. So the advantages, we could quickly mention that the advantages have, we can find the content more easily. If we can figure out the hash of what we're looking for, we can somehow route through the network to find a particular item. And the disadvantages would be that, might not be so obvious, but essentially the peers are assigned data. Yeah, so we have to impose a structure on the network now. We have to say, hey, you peers, you're at 000. You guys index Ricky Martin's new album, even if they maybe aren't interested in Ricky Martin's new album. So the peers don't have a choice here. There's a structure imposed on the network. Does internet routing work that way with a distributed index, like using IPs? It does in a sense. I mean, you have different domain name servers that, I'm not an expert in this, by the way, but you have domain name servers that essentially translate from your URLs to your IPs, and then at the internet level, you can contact that server through the internet routing to make a request. So it's maybe a little bit more. It's, in this case, the difference is it's not like a DHT. I would say it's more like a hierarchical peer-to-peer system in a sense. In that here, you're not telling different machines what they need to store, right? So in the DHT, you're somehow using it to store data, to tell the different peers what to store. So could I give an example of how this works? So let me move on. I'll present the next couple of slides in terms of the DHT, and then we'll see. So this is more detail of, this is the abstract kind of data structure, but I'll talk a little bit more about how this would work. The main thing is what we're doing here is we're telling each peer what it needs to index based on their hash. So here we have the hashes, and we have a structured DHT. So this is called a circular DHT, where each node is only aware of its neighbors. Okay, in this case, we're just incrementing the hash range in a binary way. So 0, 1, 2, 3, 4, 5, 6, 7. So this gives us ON lookups. So if we wanted to get, well, n over 2, right? If we wanted to get from here to here, we'd have to go all the way across the network, touching half the peers. So this is an example here, for example, Pixie's new album. If the hash is 111, then we would know that we need to go all the way across the circle to the other side of the network. And then what happens, they establish a direct connection, and this peer can send the data to this peer here. So, okay, this is a circular DHT, but this doesn't enable the kind of tree that we saw. So what we implement on top of that are shortcuts, which are essentially ways to skip ahead in the circle. So this allows us, for example, to, you know, if we're here and we're looking for Pixie's new album, so what we do is we'll contact the neighbor can, rather than going all the way around the circle, it can directly contact the node with Pixie's new album, get the data, and then establish the connection, for example. So these shortcuts enable this sort of this tree that we saw. So we can just connect the nodes in such a way that we can skip ahead and have you know, login style lookups. So the idea, again, why not connect everything? If we connected everything, it would be too many connections, right? So these shortcuts are somehow a balance to not have all of the peers connected, but to still enable fast communication to any one particular peer. So what happens if peers leave? This is called churn, right? So it just means that there's somehow changes in which peers are active in the network. So what we need to do then is also keep n successors. So in this case, what it means is, you know, if this mobile phone here is going to leave the network, we need to somehow be able to survive without it and keep the connection in the network. So it means that essentially, in this case, I'm not going to draw it for all of them because it would become a mess, but every peer contains not only a connection to its neighbor, but a connection to its neighbor's direct neighbor, right? So it maintains connections to several peers. So what happens if there are new peers? Well, we can use the new peers to fill gaps. And again, this neighbor now will be connected to the neighbor of its neighbor, or we can replicate. So, you know, we can just fill in the different hash ranges. We can add more nodes to those. So that's how more specifically the DHT works. I hope I answered the question about how it works in a lower level. If not, you can ask again, maybe. So the key thing here is that we're assigning peers to different hash ranges, and depending on what hash range is assigned, for example, all the things that are hashed with 110 that start with a hash of 110 will index them on these peers here. The key thing here is that we're using hashes to assign content to the peers, and that way we can find the peers with given content more easily.
Professor, I have a question about the DHT. Is that hashing just used for the first connection? Like if I want to connect to another peer, then they'll make the connection with the shortcuts that you said. And afterwards, the peers will just talk between themselves, right?
Yeah, so once the connection is established, for example, okay, I don't actually have it on the shortcut example, but essentially once all we're doing here in the kind of initial messages is we don't want to transfer data across multiple peers or anything like that. We're just trying to get the information about the, you know, for example, the IP addresses of the peers. Once that connection is established, which is this sort of orange thing here, then we establish this green connection, which would be where they actually start sharing data, or, you know, this node here starts transferring data to this node here. So it's only used for finding the location. They could conceivably store that in a cache. I think that would be outside of the DHT, you know what I mean? But you could imagine in an application caching some information about peers that were or have been, you know, connected with in different ranges.
Okay, thank you.
Okay. More questions or doubts? Okay, So let's talk about a real system, a real distributed system. So, if we talk about BitTorrent, BitTorrent is sort of the classical peer-to-peer file sharing system, right? But it's not entirely peer-to-peer. So what I really want to get across through this example is, okay, a little bit about how the distributed system works, but also the fact that these pure abstractions often, practical systems will use a mix of different elements of these architectures. So BitTorrent, how does BitTorrent work? What is BitTorrent? BitTorrent is essentially a file sharing peer-to-peer-esque service where people can somehow share data directly between each other, and the data is never stored in a central server. So how does it start? It starts with some peer. Here it's kind of, I took this diagram from Wikipedia, in fact, but here it's shown as a different kind of icon, like a desktop, but it's not any special kind of peer or anything. It's just the one that happens to have the data, right? So the data in this case is the Ricky Martin's new album, and the data will be divided into blocks, into chunks of data, right? So we could think about maybe we have 6 chunks here, maybe for 6 different songs, or just chunks of 10 megabytes or whatever. So the block size depends on the overall size. So essentially this peer here that has this data and wants to share it in the network has to upload a description of the data, which is stored in a torrent file. And that needs to be stored in a central server where people can search for that information. And we'll store information about like the size of the torrent, some initial information about what trackers to use, which I'll have to discuss in a second, and some metadata. What are the file names? What would the directory look like? And what are the file sizes and so forth. So this is just a metadata file called the torrent file that describes somehow some information about the data. It does not contain the album itself or any music or anything like that. A very small description of what the peer wants to share. So later, if a peer is interested in Ricky Martin's new album, they can search for Ricky Martin in the BitTorrent search server. So examples of this would be, for example, the Pirate Bay. There's various others. So they receive the torrent from the search engine, BitTorrent, the torrent file search engine. So they fetch the torrent file that was originally shared by this peer. And then essentially the torrent file itself doesn't contain any information about the peers, but it contains information about what's known as a tracker. And the tracker is the component that is responsible for saying which peers contain which data or which peers are looking for which data, right? So this tracker is sometimes centralized, like on a server. There are various central kind of peer trackers there are several available and they all more or less do the same thing. Or there is the option of using what we've seen, which is a DHT, a distributed hash table. And this distributed hash table is something that's coordinated amongst the peers that are operating in the network, and it stores information about which peers are active. So what does this tell us? This basically here contains information about which peers are connected to the network. And as more peers connect, then this tracker will keep track of who is looking for what data, what their IP addresses are, what clients they're using, and which blocks they have, I believe. So which blocks of the data we currently have. So again, this is its own system here, right? This can be central client server, or this could be a structured peer-to-peer, which is the case for a distributed hash table. So then the file sharing begins, where there is these peers start to share blocks of data, and it's not that they're being shared from the source, but rather once a peer gets a block of data, it can serve the data to other peers that don't have that block of data. And BitTorrent uses a certain algorithm that ensures that rare blocks, essentially blocks of the data that are not common or that few peers have, will be the priority to share. So this ensures, for example, if there's only one copy of a block and that peer goes down, then nobody will be able to complete the file, right? So the torrent protocol has various algorithms to do so efficiently, to be able to efficiently share the data in the network. And ensure as well security in terms of, not security, but ensure that there is at least one copy of every block to try to maximize the probability of that happening. So then essentially this here is a sort of a more classical peer-to-peer system where the peers are sharing data with each other, blocks of data. And then once they have finished, they can become as well what we would call a seed. So if you're looking for data, you're leeching. And if you have all the data and you're providing it to somebody else, then you're seeding. So this is a pretty robust protocol for file sharing. So in summary, the uploader creates a torrent file, which is a description of the data to be shared, uploads it to a torrent file search engine, for example, announces on the tracker, connects to the tracker and announces on the tracker that they're connected, monitors for downloaders, somehow keeps tracking, looks on the tracker and checks to see who's connecting, connects to the downloaders, and then starts sending parts of the file, prioritizing parts of the file that have not been shared with many peers. The downloader searches for the torrent file in the search engine, downloads torrent file, announces to the tracker, monitors for peers and seeds, connects to those, and then sends and receives file parts. So the other thing to mention is you're not just kind of leeching, you're not only downloading, but as you download and complete a block of data, you can also share that with other peers. And here we see the different categorizations, and that this can be considered client server, this can be considered structured peer-to-peer if it's a distributed hash table being used at least, and this is a more direct peer-to-peer where you're just contacting peers that have the data or need the data directly. And last part, watch is the legal movie downloader. So of course, BitTorrent is also used for very valid applications like sharing massive files relating to distributions of operating systems or massive files that would just be infeasible to host on central servers. But yeah, okay, so any questions on BitTorrent? Why am I speaking specifically about BitTorrent? What I really want to get across is the idea that no one system, distributed system, will fall very neatly into these abstractions. So there will be elements that are maybe client server, more elements that are more structured peer-to-peer, elements that are more direct peer-to-peer. Right? So complex systems will have different components, and those different components might use different types of architecture. Okay, so if there's no question, we'll go on to the real world. So there's three types of location in terms of how distributed systems are hosted that we can talk about. We can talk about cluster computing, which is typically referred to as machines in a central local location. For example, a local area network in a server room. So for example, I'm in the university, downstairs I've got my cluster of 5 machines, and they're all connected by network, and I'm running my distributed system on these 5 machines, right? So this would be sort of cluster computing. So this typical sort of scenario here, where you have, okay, this is more than 5 machines, but maybe you have something in a university or you're in a large company that has its own cluster. Second type of computing would be known as cloud computing. And this is where you have machines that are typically rented and are typically in a central remote location. So an example of that is Amazon EC2, Google Cloud, and so forth. So what happens here is you have your client, but all these machines are in a remote location. You're probably renting these machines, and you're running your distributed system remotely through the interfaces provided by the cloud provider. A third idea would be, okay, sorry, as well, just to mention that in cloud computing, it's not necessarily the case. I mean, in terms of centrality, you could have a distributed system working in Amazon EC2, for example, that actually has components running in different regions, right? So you could have machines in the US and machines in the EU or machines in Asia or Africa or wherever. So what is EC2? I don't actually remember what it stands for or if it stands for anything interesting, but it's essentially a service provided by Amazon where you can rent machines, you can rent servers, you can rent physical machines, and you can run applications on that. So you could run, for example, a website on that, or you could run a massive data analysis on that. Elastic computing, thank you. So you can rent more machines as you need them, or you can rent fewer machines as you need to. So that avoids you, if you're working in a company, a small company, for example, that occasionally needs a lot of computing power, it avoids you having to manage those machines or pay for them, their physical hosting. And Amazon is just one example. There's also Google Cloud Services, and I think Microsoft, how have I forgotten the name? It's not Azure, is it? I should know. I don't. So I think Microsoft also offers a similar cloud service. Azure, okay, it is. So we have machines in the third type of distributed system we have in terms of physical location would be grid computing. So in this case, what happens is we have machines in diverse locations. So it's essentially your more kind of pure peer-to-peer type system-ish. Actually, I think I might retract that, and I would say that it could also be a client-server architecture, but you have all these different peers in different locations, and they have different types of machines. You could have big machines, small machines, mobile phones, whatever, and they're all somehow participating in a distributed system. So an example of that would be these sorts of volunteer computing projects where you can install some, these are still very popular, but they became all the rage, as screensavers for desktops, where instead of just running a desktop, you could run a climate simulation, for example, using the idle computation of your computer. While you're not using your computer, when the screensaver kicked in, you would also start to compute, for example, a branch of a climate simulation and report back to a central server the results of the computation. So you might recognize this number, you might not. This is a prime number. This is in fact a Mersenne prime, so 2 to the p minus 1, where p is also a prime, maybe prime. And this is the largest prime number that has been found. That was found in 2018 using a grid computing project called PrimeGrid. So there are various projects for finding different types of primes. And these are based on grid computing. So they're based on this idea of volunteer computing, that people volunteer some of the computation power they have. Of course, this computation is not free. It has an energy cost, it has an environmental cost, and so forth. But if you feel it's a good cause, you can volunteer some of your computing time on your notebook, and probably on your mobile phone and your Raspberry Pi to these sorts of projects. So to summarize, we have cluster computing, which is typically centralized but local. We have cloud computing, which is centralized but remote, and we have grid computing, which is decentralized. So we have all these peers in all these different locations, but remote. So I guess we're out of time. So we'll talk about I'll give an introduction to the lab, which will be quite fitting maybe. So I'll finish the class and I'll talk about what we'll be doing in the lab next week. But the idea would be that you implement a messaging system, which is an example of a distributed system. So before we go on to see all these distributed frameworks and platforms for processing lots of data or indexing lots of data, I think it would be good if you have an idea of the basics of like how you would implement a distributed system, knowing, a bit of Java or whatever programming language, how are these things coordinated? So we'll talk about Java RMI, remote method invocation, and how we can essentially call Java, we can coordinate Java programs across different machines. But we can stop here for now. Any questions or comments?
Profe,
Yep.
estaba pensando hace un rato si que podría existir una red P2P pura.
Una red que pura. No entiendo.
Pure, pure. Pure
Yeah, pure.
P2P
Okay.
network. Porque,
Yeah.
porque
So
lo que
the
estamos viendo es que siempre se requería también que fuera una parte cliente-servidor.
centralizado.
Sí, sí.
Claro, claro. Sí, sí, sí. So the closest we can get to a pure, like peer-to-peer network, I think I've gone too far, is the unstructured. So you can do it. There's no problem. And maybe even it would be the practical choice if it were very difficult, if it were very costly or impossible to really have a central service. Sorry, let me find I went way too far here. So this would be the purest. This would be where you connect to your neighbors, your friends or people in your neighborhood or people you can talk to physically, and you get their IP and you bring their IP home and you connect to them. And there's no central coordination here whatsoever. And in this case, the issue is that somehow if you want to find something, your only way of communicating with the other nodes in the network is through contacting your neighbors and getting your neighbors to contact their neighbors and getting those neighbors to contact those neighbors. So it can be highly inefficient. It can be highly inefficient in the sense that for every request, we have to send in the order of ON messages, where N are somehow the number of peers connected in this sort of connected component of peers. So this is as good as we can do in terms of, this is the purest we can get a peer-to-peer system. To make it something more efficient than that, we have to either impose a structure on the peers and tell them what they are going to index, right? So somehow every peer can based on the hash, know what range of peers, where in the network the data might be. Or we need to use some sort of central or super peers or some sort of bigger nodes that contain more data than the rest of the peers. So it is definitely possible. You can definitely implement this peer-to-peer network where there's no peer that has any, there's no node that has any particular responsibility. Every peer is kind of equal. Nothing is forced on anybody. They can index, for example, whatever content they want. They can, they can share with whomever they want. But the problem is just the cost. The cost is, you either are connected to everybody and everyone knows, everyone is connected to everybody and knows what everyone is indexing, or you're only connected to your neighbors, and it's very inefficient to find something. So I don't know if that answers your question.
Sí, sí.
Okay. So there's a comment, grid computing for climate change simulation sounds kind of ironic. That's true. I don't know how much computational power. I guess it's a cost, right? You invest a certain amount of energy now to better understand the climate and maybe convince other people not to, right? Maybe you increase awareness, and in that way you can improve the situation, even though it has an initial cost. I guess that's the argument that they would make. But to be honest, I'm not sure about the costs of grid computing for how much is used for climate change. Of course, if we start talking about Bitcoin, the mining for cryptocurrencies, but Bitcoin in particular, I think the energy used, it would be sufficient to power Argentina. And this for an artificially difficult problem that has no purpose. So yeah, this is another issue. So I think Bitcoin is based on proof of work, where you need to do lots of computation to somehow make the coins rare, but there's also models looking at proof of stake instead, which would be better for the environment. POW, proof of work. Yeah, probably is stupid. Probably it is stupid. Well, if you can replace it with proof of stake or something that does the same thing but doesn't require the energy consumption of Argentina to run, then I think that will be a win for everybody. Yep. So POW stands for proof of work, which is used in Bitcoin, used in most cryptocurrencies. It's essentially a way of ensuring the rarity of the currency. If people could mine Bitcoins very easily, then you would have lots of competing blocks being produced at the same time, and you would have you would have a unpredictable supply of Bitcoin. And if you have an unpredictable supply of Bitcoin, then its value will fluctuate a lot. So Bitcoins are mined, blocks are mined every 10 minutes in Bitcoin, and it's made artificially difficult. So something is mined every 10 minutes, so they know exactly how much supply there will be for Bitcoin until the end of Bitcoin. And other cryptocurrencies do something similar. So not so related to distributed systems, more to do with cryptocurrency, I guess. But the alternative is proof of stake, but that's another topic. More questions or comments? Okay, so we'll chat on Wednesday in the lab. So we'll finish the class and then we'll do a lab on Java RMI. Okay, so see you on Wednesday.